Okay then, good evening to all of you. So welcome back again to the fifth week of the problem solving session for the fluid mechanics for the course fluid mechanics and its applications. So uh, in the last session we were discussing about Bernoulli's equations and its applications, and we could discuss thoroughly that we were able to discuss thoroughly about the Bernoulli's equations and the important assumptions that must be taken for the validity of the Bernoulli's equation. So just for the sake of revision, I would just like to write the Bernoulli's equation once again. So it's just given by P by rho g plus V square by 2g plus Z is equal to constant. Given constant along a streamline, given the flow is steady, incompressible, inviscid, and obviously along a streamline. No heat interaction, say again, no heat. So I don't have a space for that, so I will just so these are the assumptions that was taken for the derivation of the Bernoulli's equation from the energy equation. This is basically from the first law of thermodynamics, considering the various types of work and heat interaction that can be achieved. I won't say work, say heat interaction. Work interaction in the sense that many types of works we are ignoring, but not all kind of work. So we need to consider that. So yeah, no heat interaction, say, and some additional or external work interaction we are neglecting. Okay, so these are the assumptions that we should take into consideration before applying this special form of the Bernoulli's equation. Okay, this is a very special form, or the most well-known form, but the thing is, it's also the most exclusive form, in the sense that only after the satisfaction of these assumptions this equation turns out to be valid. Okay, so we discussed about it thoroughly in the previous week's session. So today, and since we are left out to solve some questions on Bernoulli's equation, so we will start with solving some questions, some simple questions regarding the basic application of this form of the Bernoulli's equation, and then go on ahead with this topic's discussion. Okay, so let's go ahead and take this question. So here it's given that a tornado may be modeled as a combination of vortices with VR and VZ equal to 0, with VR and VZ equal to 0, and V theta is equal to V theta, which is a function of R, where V theta is a function of R, such that V theta is given by omega R for R less than the radius of the tornado. Okay, and omega capital R square by R for the region outside the radius of the tornado. Okay, for R greater than R, it is V theta is equal to omega capital R square by R, and for R less than R, it is omega R. Omega is smaller. Sorry. Okay. Then assume the flow to be inviscid and the fluid density to be constant. Also neglect the effect of body force due to gravity. It's told that we need to consider these assumptions from the start itself. Find the regions in the flow field where the flow is rotational or irrotational. So we need to find the regions in the flow field which are where the flow is rotational or irrotational. So we need to define those regions. Okay, whether the inner zone, whether the inner region is irrotational or the outer region is irrotational, or the both regions are rotational, or either both regions are irrotational. So we need to find it, and to find that we know that to find the rotational, to find whether the flow is irrotational or rotational, we need to find the curl of the velocity field, right? We need to find the curl of the velocity field and have to find whether it is equal to 0 or not. If it is equal to 0, then it is irrotational. And if it is not equal to 0, the flow field is, or the velocity field is rotational. Okay. Okay. So keeping that in mind, we go ahead and find the curl of the velocity field given to us. So it is del cross V. So this is the special form of the determinant that arises in the form of a cylindrical coordinate system. So given the fact that a tornado may be modeled, maybe ideally modeled by the help of a cylindrical coordinate system, so that's why here as my own choice, I have chosen the cylindrical coordinate system, the determinant, basically this nebula operator or the curl operator this curl of velocity, the operator that acts on the velocity vector. To find that curl, I have used its components from the cylindrical coordinate system. So as I mentioned, even though it is given, the velocities are given in quite obvious, are based on the radius of the tornado, and it looks quite obvious that it should be a cylindrical coordinate system, or maybe spherical if like somebody is not specifically knowing about it. But it is also the same solution can also be modeled in the form of in Cartesian coordinate system as well. So by modifying or playing with the terms with the terms the terms in the given in the equation. So representing radius is as the square root of x square and y square. So depending on the coordinate system, your equations will also change. But since it is the most simplest form is to choose a cylindrical coordinate system to solve this equation, so I have chosen a cylindrical coordinate system. So let me just write it in cylindrical coordinate system. See, I am emphasizing it so much so that we can get an idea of which coordinate system would be most suitable for our to find a solution. So that's why I am emphasizing these facts again and again. So okay, so given that we find the curl of the velocity field, so just substitute the value of v theta, Vr and Vz in the equation. So we know that Vz and Vr are equal to 0, and we substitute the value of v theta here. So substituting the value of v theta, we get omega r square. Then just evaluate this determinant. So we get that del cross v is equal to 2 omega z. Okay. So it basically means that the velocity field in the inner region is rotational. So just write it. Inner region, it is rotational. Okay. So following the similar steps, we check for the outer region where v theta is equal to omega r square by r. We substitute the value of v theta here. So we finally get that the curl of the velocity field in this case equal to 0. I have not done the complete calculation here again. So you can just do that. So you find it as for the outer region, it is irrotational. Okay. So for the this first part of the question is at least solved. That we have found out which among the two regions are rotational or irrotational. So we find that the inner region is rotational and the outer region is irrotational. Okay. So again, the continuation of this equation question will be. Extremely sorry for this additional this noise. So stop for some time to see that whether this noise gets mitigated or not. So okay, I guess we can continue now again. So the continuation of this question is that now consider 2 points. A is equal to 3r by 2, where 3r by 2, A where r is equal to 3r by 2 and theta is equal to pi by 6. This is the first point in the tornado, say, and B is then another point where r is equal to 2r and theta is equal to pi by 4. Okay, in the flow field. Find out the correct pairs of statements. Okay, so here we have the point B lies on the streamline passing through A. Okay, this is the first statement. Point B does not lie on the streamline passing through point A. Okay, it's contradiction of the first point. Then Bernoulli's equation can be applied between points A and B to evaluate the pressure difference between them. Then again, the Bernoulli's equation cannot be applied between points A and B to evaluate the pressure difference between them. Okay, so these are the given statements. So since we know that since we are asked to find whether these 2 points lie on the same streamline, so it basically tells us that we need to find out the equation for the stream function, because stream function is a mathematical way to find out the equation for the streamlines in the case of a 2D incompressible, steady incompressible fluid flow. Okay, so since it is already given that the flow is incompressible and steady and 2D and essentially now 1D because there only is one velocity component, so the definition of stream function still holds. So we can now apply stream function to find the equation of the streamlines, so that we can check whether these 2 points lie on the same streamline or not. Okay, so we are given that we know that for cylindrical coordinate system the stream function can be represented as ur is equal to 1 by r d psi by d theta, and u theta is equal to minus d psi by dr, or dou psi by dou r. Sorry, it is partial derivative, so I should say dou psi by dou r. Okay, so since we know that u theta, ur is equal to 0, it is given for the for this current problem, ur is equal to 0. So we have u theta. So now we know that for the outer we need to check whether the given points lie on the inner region or the outer region. So since it is given that let me go back. Since it is given that for r greater than r it is omega r square by r, and for r less than r it is omega r. So we have to check whether the radial distance or the radial distance of these points lie from the center are less than r or greater than r. So we can clearly see that both the radial distances are a distance greater than the radius of the tornado. Okay, so the first point is at the distance 3 by 2 r, which is basically 1.5 times the radius of the tornado, and the second point B is at a distance 2r, so it's basically the distance 2 times the radius from the center of the tornado. Okay, so we see that both the regions are, since both the points are out in a region, both radial distance of both the points are at a point greater than the radius of the tornado, so we can we can have u theta as omega r square by r. So we just substitute the value of u theta as omega r square by r, so we get that minus dou psi by dou r is equal to omega r square by r. So then we can integrate this equation to find. I have just done the same thing from the verified the same thing from the continuity equation. So just to verify it, so I have checked it again. So we achieved the and just to make just to make sure that this we have done for so that we will get the same outcome, that we finally get that our psi is a function of r only. Okay. So having okay, I'm sorry, I'm really sorry. So we need to do this step so that we can check whether our stream function is only a function of r or not. Okay, why it is necessary? So that we can have a the integration process to be much simpler, so that we could deal with complete derivatives rather than total derivatives. Okay, so now we look into the continuity equation. I'm sorry that I was confused in this part, so I apologize for that. So we need to look in this we need to look into the continuity equation. So I was just a bit confused after looking at this outcome. Okay, so from the continuity equation, this we get that ur is equal to 0 and uz equal to 0. So only this portion of the equation remains valid. So it is given that dou by dou theta of u theta is equal to 0. So we get that u theta is not a function of theta. Okay, and again dou psi by dou, basically u theta is omega r square by r, right? So we have this. So we get that since u are equal to 0, since you are equal to 0, psi is only a function of r, right? How we get this? It's very simple. Okay, since u are equal to 0, we get that we can write ur is equal to 1 by r dou psi by dou theta. Okay, and since u are equal to 0, so dou psi by dou theta is equal to 0. So psi is only a function of r. So this we get. So that now we can change this partial derivative into complete derivative. So we do the same. We can write now d psi by dr is equal to minus omega r square by r. So now we take, just for the sake of simplicity, we can take minus omega r square by r as some constant. Okay, we take it as c. So we get minus we get d psi is equal to c dr by r. Okay, now after the integration we get that psi is equal to c ln r plus c1 some arbitrary constant. It's not a function of theta or r. Okay, because if seeing that psi is only a function of r now, and since we get that, we can clearly see that psi is only dependent on r. Okay, so even if we don't go up to this step, we can, from here itself we can see that psi is only a function of r. Okay, and now since both of these points have two different radial distances, the radial distance of these 2 points are different, so we can clearly and since theta has no role in defining the equation for the streamline, so you can see that the streamline only depends on the radial distance from the center of the tornado. Okay, so it basically tells us that these 2 points, since they are at different radial distances, these 2 points should lie at 2 different streamlines. So these 2 points are at 2 different streamlines. So we can conclude that A and B lie on 2 different streamlines. Lie on 2 different streamlines. So that's sorted out. So we can see that point B, you can see tell that point B does not lie on the streamline passing to point A. So this is the first characteristic. So now again we know that Bernoulli's equation is valid only for 2 points that lie on the same streamline. But again we need to check whether the flow is irrotational or rotational, because we know that if the flow is irrotational, then the Bernoulli's equation can be applied for any 2 points in the flow field. Okay, but now again we see that since both these points lie on a region greater than the radius of the tornado, so we see here that for the outer region the flow is irrotational. Okay, so now since the flow is irrotational, it is immaterial whether the 2 points lie on the same streamline or not. So we can, so here in this case now we can apply the Bernoulli's equation for any 2 points in the flow field. So we can conclude that the Bernoulli's equation can be applied between points A and B to arrive the pressure difference between them. Okay, so this is what we had to find. So 2 and 3 are the pairs of the 2 correct statements. So we got that. So now we proceed ahead. So again, so this equation is again is the basic application of the Reynolds transport theorem. So I guess this was left out for the previous week session, and since the previous week we were also dealing with RTT as well as boundary equation, so this question was left out. But okay, I can go through it. I'll go through it a bit fast because for the sake of time. So okay. So we are given this question. It's quite pictorial, so very less details are explicitly given. So it is shown that given that there is a funnel, a conical shaped funnel, I can say, where the liquid, this region, this particular region, so shows the liquid that falls through the lower opening of this funnel with a velocity v, where it is told that v can be taken as uniform through this exit. It is mentioned, explicitly mentioned here, where v is equal to 2gl and it is a constant, right? You can take here g as constant, okay? And again it's given that rho is also constant. So we need to find the rate of change of height of this, like this height, while this liquid pours out from the exit at the bottom of the funnel. Okay, so we need to find that the rate of change of height of the liquid level in the funnel. Okay, so we again just directly apply the mass conservation here. So mass conservation from RTT we get that dm by dt for the system is equal to rho by rho t integral of rho dv. Again I am sorry, I am missing the control component part here. Rho dv plus integration over the control surface rho into vr dot n cap dA. Okay, so here again for mass conservation we know that since there is no mass being created here or destroyed, so here dm by dt of the system is equal to 0. Okay, so okay, we now just define our control volume here. So this region, actually this should be a conical shaped control volume, but for just for the case that it is 2D, so we define our control volume as this this red dotted line. So this red dotted line defines our control volume, where capital R denotes the radius as the radius of the cone, the bigger the radius of the cone. Okay, so the bigger the radius, like this basically the inlet. So if this was the inlet, so this is the radius of the cone, and smaller is the radius of the cone at the exit. Okay, so given that we have since rho is equal to constant, so rho can be taken out, and integration of dv will basically give us the volume of the our control volume. So it is rho dou v by dou t plus, again it is, since there is no influx of mass here, only the fluid that was being stored here is being exits through this lower end of the funnel, conical funnel. So there is no inlet. So this term can be simply written as this. Okay, where pi r square gives the area at the exit, v is the velocity exit which is taken to be uniform. That's why this can be directly taken out the integral, and rho is taken to be constant. Okay, again this v, the volume of this our control volume can be taken as 1 by 3 pi r1 square h. Okay, so this is the volume of the control volume. So here, so this region we define as a control volume because control volume is continuously changing with time. So I am sorry, I just previously I have defined this region as the control volume, but sorry, actually this blue region, this region containing the fluid should be ideally defined as control volume, because our control volume is changing with time. So That's why this region will this blue region, this region can be taken as our control volume, so it will change continuously with time. So so the volume of this region can be taken as 1 by 3 pi r1 square. It is again an approximation. We are ignoring, assuming that this the volume, the area of the exit is much smaller. So we can directly take it as we can approximate it as a cone. So the volume of cone is given as 1 by 3 pi r square. So we take that assumption. So V is taken as 1 by 3 pi r1 square, where r1 is the radius at this point. Okay, the radius of the cone. So again, so we have here now we can see that we have two variables, right? R1 and H. So and since it is dH by dt that we have to find, so it should be quite convenient if we could eliminate R1 from the equation, right? So it would be better if you could represent R1 in terms of H. So we just use the principle of trigonometry and find that tan theta is equal to R1 by H. So we can clearly see tan theta is equal to R1 by H. So given that, we can substitute this value in the substitute the value of R1 in this equation, and then we find that dou v by dou t can be represented as then substitute the value of v in this equation. So we can, dou v by dou t we can obtain as 1 by 3 pi 3h square dh by dt tan square theta. So basically take the derivative. So we take the derivative of h with respect to t, and we then equate this with the net efflux. Okay. So after doing some certain manipulations, we can finally get that dh by dt is equal to minus ver square by h square tan square theta. Okay. So this is what we obtain. So again, as I told, we were explicitly dealing with the RTT and the boundary equation in the previous session. So these were the questions that were left out. So I guess I will skip this question. It's a very quite simple question. Again, simple application of mass conservation. So I will skip this question for the sake of conserving time, and go ahead with this week's contents. So again, in this week we were dealing with further applications of boundary equation. So we are checking how this boundary equation could be extended to other problems where those four exclusive assumptions can be eased out. Like we can generalize the application of our boundary equation by excluding some of those assumptions, so that the range of application of boundary equation can be increased. Okay, so it's basically we can say the extension of the application of the boundary equation. Okay, so here one of the application again that was discussed by Professor Gupta in the video lectures was finding the pressure distribution on a cylinder in an in-viscid flow. Okay, in an in-viscid flow. So here for a flow over a cylinder from the in-viscid flow, the stream function is given as V naught 1 minus r square by r sin theta, where r is the, let me just draw it, where r is the radius of the cylinder and V naught is the free stream velocity that approaches the cylinder. Okay, so we can just assume that V naught. Okay. And the radial velocity can again be given by 1 by r dou psi by dou theta, where in this case the radial velocity at r equal to r for any theta. Okay, so I guess I should represent theta as well, just to clear. This is theta and this is r. Okay, so the radial velocity Vr at r equal to r and for any theta is equal to 0. Why? Because since we assume that our cylinder has a solid surface, so there is no passing of fluid inside the surface of the cylinder. So here the no penetration boundary condition is applied. So even if the flow is inviscid, the no penetration boundary condition still holds, because the fluid cannot enter the surface of the cylinder. But since the flow is inviscid, there is no point of having considering the no slip boundary condition. So the no slip boundary condition is neglected in the case of inviscid flow. So we have v theta, it is the angular velocity component. V theta is equal to v theta for at r equal to capital R for any theta is equal to minus dou psi by dou, which is given by minus 2 v naught sin theta. Again, how we have derived this form of stream function, I guess we will deal separately in the later part of the course where we will be discussing our potential flow theory. So this you just take for granted for right now, that stream function in the case of flow over cylinder can be given as this equation. Okay, so this we just found out by finding the derivative with respect to r. Okay, so this is quite simple. So given that we have the velocity of the velocity of the flow at the surface of the cylinder for any theta, okay, because it's valid for any theta. So now we can apply the boundary equation at the 2 points in the flow field. Okay, so we assume that there is a streamline of this form. So it's not quite visible here. So let me just try to draw it so that it's not confusing. So we just assume that there is a streamline of this form. Because here we have not derived or proven that the flow is irrotational. So once we prove that, then we need not to worry about whether the stream the 2 points line along a streamline or not. But since we have not yet proven that the flow is irrotational, so we need to consider that these 2 points lie on the same streamline. So now, if this red line, let me zoom it a bit. So if this red line represents streamline in the flow field, so we can here this it is not quite. It seems that it's quite close, but just for the sake of simply saving space, I have drawn this point 1 to be quite close to the surface of the cylinder. But ideally, this point can be taken a bit further, where the disturbance generated because of the surface of the cylinder is not felt by the flow field. So it basically remains uniform. The flow basically remains uniform at a distance quite farther away from the surface of the cylinder. Okay, so if this point is taken sufficiently away from the surface of the cylinder, we can consider the velocity at this point to be equal to v naught. Okay, so v1 is equal to v naught, then p1 is equal to p atm, and v2 is equal to minus 2 v naught sin theta, and v2 c. Since there are only two velocity components and one of the velocity components is 0, that is Vr is equal to 0, Vr is equal to 0, so we have v theta. So v theta is the only velocity component that exists. So v2 at point 2 is the angular velocity component, so that is minus 2 v naught sin theta, which we found out from the string functions. Right, now we need to find out p2. So we apply boundary equation at these 2 points, and we finally get that p1 minus p atm is equal to just playing with the terms of the boundary equation and just modifying it. So we get that p1 minus p atm is equal to 1 by 2 rho v naught square 1 minus 4 sine square theta. Okay, so that's what we get. So okay, I'm sorry, it's not p1, it's actually p2. So it should be p2. p2 minus p2 is equal to 1 half rho v square 1 minus 4 sine square theta, and assuming that this distance this height is not that quite significant, so we can just get that p2 is equal to p atm plus half rho v naught square 1 minus 4 sine square theta. Okay, so again by the definition of the coefficient of pressure, we get that Cp is equal to P2 minus P atm by half rho v naught square is equal to 1 minus 4 sine square theta. Okay, this is quite a very standard result in the potential flow theory. So we will, when we will discuss it, we will see how these flow fields are obtained using stream functions and the potential function. So let's not go discuss it right now. So and we will eventually see how the stream functions are generated by considering the sum of, say, a source and a sink like this, or So okay, we'll look into that while discussing. So right now we'll just take the given stream functions for granted and find the required velocity components of it. So this is the coefficient of pressure. So just if you need it, we need to write it. Coefficient of pressure. Okay. So now okay, so this part again I would like to skip for the sake of saving time. The flow or pressure distribution on a rotating cylinder. So similar to the previous case, the stream function are given to us. We just need to find the velocity components. Again, since the surface of the cylinder is impenetrable, so there will be no flow across the surface of the cylinder. So again, the radial velocity component will be 0. So we will have only the angular velocity component. So we use that. We apply apply the Bernoulli's equation and find the coefficient of pressure. Okay. So this I will just skip for sake of saving time. So now we discuss a bit about flow through open channels. So again in this case we'll discuss the flow over a wire. So just consider this. So basically in the front view, you can just assume that the flow is approaching in this forward direction through this, and we have this certain shape of confinement. So we can assume a square shaped wire. So where the point of contact of the liquid is in a it should be actually rectangular, but we just say for the sake of simplicity, we can say this shape is in a square shape. So assuming that in this case, so now we try to find out the flow rate through this wire. Okay, wire. So should write that down, wire. So wire and notches are basically like have the same geometrical structure, and just the size of it is just the size that vary. Okay, so notches, like if we are using for a very small scale, say flow through some pipes or ducts, if you want to measure in a very small open channel flow, if we want to measure flow rate through those open channels, so there we can take it as notches. We tell those openings through that open channel as notches. Okay, since it is very small. But if we are now dealing with very large scale notches, like for say flow through a dam or a very large open channel, large scale open channel. So to say flow through a canal, we are measuring the flow rate through a canal, then we use the term wire. Okay, so the geometrical shape or structure of these notches and wires are exactly the same, just the range of application, the length scale of application varies, so that's why we have different names. Okay, so given that, now we see how to find the flow rate through this wire and notches. So the derivation is exactly the same, because since the geometrical structures are exactly same, so assuming a square shaped channel, so square shaped notch, so flow can be to any shaped channel, but the shape of the notch determines the expression for the velocity or the mass flow rate, so volume flow rate. So that's why I was telling that. So given that the shape of the notch is square in shape, so now we apply the Bernoulli's equation at 2 points in this wire. So here we consider this diagram, and B is taken to be the width of the notch, okay, or wire. Okay, so the width, perpendicular width or depth. Okay. So we consider this as point 1 at a depth of h from the free surface. Again, I guess I should draw the notation to denote it as a free surface. So h can be considered as the depth of point 1 from the free surface. Then again we consider point 2 just past the wear. Okay, just past the wear. So this point 2 is just past the wear. So, and these are the dimensions. So capital Y is the height of the free surface from the datum. Okay, h is the width of the liquid jet that falls out of the notch or the wear. Okay, so and small y is the distance of this or I should say ideally h minus y. This will basically be this will basically be h minus y is the distance of point 2 from the free surface of the liquid. Okay, so given the geometrical definitions, we can take v1 to be ideally to be equal to 0, because since the depth is quite high, say the depth is quite high, so we can take that velocity at point 1 to be ideally to be equivalent to 0 compared to velocity at point 2. Okay, so see the range order of magnitude of the terms matter a lot in the scope of engineering. Okay, so the very foundation of a very important, what to say, integral part of fluid mechanics, that is boundary layer flow, is dependent on the order of magnitude of the velocity components. Okay, so given that in mind, we can say that even though this is may not be equal to 0, but ideally if the flow is through a very small channel, so this cannot be equal to 0. But given that compared to velocity at point 2, v1 is much smaller, we can like ideally just take the velocity at point 1 to be equivalent to 0. And in the case of wears where the depth of the channel is much higher than much higher, so the velocity at point 1 can ideally be taken as to be equal to 0. But just for the sake of so just for you are not confused, we take v1 equivalent to 0 because order of magnitude of v1 is much smaller than order of magnitude of velocity at v2. Okay, of v2. So that's why we can ideally take v1 to be equivalent to 0. So keeping that in mind, then we have P1, the pressure at point 1 to be rho gh, because if it is if v1 is 0, then we can take the flow to be ideally to be steady, and the flow is static, and then if the flow is static, the pressure at point 1 can be ideally given by the hydrostatic law. So P1 pressure at point 1 is given by rho gh. Okay, it's the depth of the point from the surface of the free surface, and then just with some geometric manipulation we get that z1 would be equal to y minus h, okay, this distance. So substituting that at the in this equation, we get that v1 is 0, so this is 0, so z1 is equal to y minus h, and p1 g minus by rho g would be h, right? Just divide this by rho g, so we have v1 square by 2g plus z1 plus p1 by p1 g rho g is equal to y. Okay, again we follow the same similar procedure from point 2. v2 is now non-zero, so we cannot directly take it to be 0. We now have to play with the these two terms, so we can take it as z2 would be equal to z2 would be equal to y minus h, so y minus h plus y, and p2 can be ideally be taken to be 0 because we assume that the the flow from the notch or the wear comes out as a free jet, comes out as a free jet. So pressure at this point can ideally be taken to be as atmospheric pressure. So keeping that in mind, so we have v2 square by 2g plus y minus h plus y is equal to capital Y, which is obtained from this first equation. Okay, so we now equate these two terms. So we get that v2 square by 2g is equal to h minus 1. Then v2 is equal to root 2g h minus y. Okay, then again the mass flow rate can be obtained by dq is equal the mass flow. So if we try to integrate this, we need to find the mass flow rate through this square shaped notch or rectangular notch. So here we take an elemental area, where the area of this elemental area would be equal to b dy, right? So it's better if I just draw it. So if we take it as dy, the area of this elemental area dA will be equal to b dy. So we may ask why we are doing the integration. See, because v2 is not a constant now, because ideally you always found that for the case of in viscous flow, we ideally found that the velocity remains uniform at the exits, right? But since here v2 is a function of y, we cannot directly substitute it in the equation like q is equal to ab, right? So this is actually a function of y now. That's why we need to do the integration to find the volume flow rate at point 2, right? So this would be the elemental volume flow rate through this elemental area, and to find the net volume flow rate we just do the integration from 0 to h. So if we take this as equal to 0, then the height of the liquid at the notch to be equal to h. So say it is z equal to h. So we do the integration from 0 to h, then we finally find that the net mass flow volume flow rate is equal to 2b by 3 root 2g h to the power 3 by 2. And again for say to this volume flow rate may encounter some certain modification because of the certain losses that we are neglecting in the case of real fluid flow. So just to have the correction, just to have the required correction so that we can get the actual volume flow rate through this notch, we use an additional term known as the discharge coefficient, because there can be various types of losses. Okay, that has been discussed in the video lecture, so I suggest that you go into that. So just to compensate those losses, we use some additional coefficient known as the coefficient of discharge, so that we can get a more accurate value of the volume flow rate through this notch. Okay, notch or weir. And this coefficient discharge are found out experimentally by various experiments, and those are the standard values that we take to find the volume flow rate. Okay, so this will be mentioned in all the questions that you are given, or if there's a standard value given in the textbooks, you can take that into consideration. So okay, again you can do the similar derivation or similar approach. You can take similar approach to find the discharge through a V-shaped notch. Okay, I again told that the shape of the channel doesn't matter, the shape of notch matters. So the shape of notch differentiates the way by which the differentiates the expression of the volume flow rate. Okay, so since the shape of the notch is changed now for the weir, so the expression for the volume flow rate through this V-shaped notch can be given by this. Okay, where alpha is the angle at the vertex. You can say vertex by the of this V-shaped notch. So again this part, I guess we just see that there can be many instances where there can be misapplication of Bernoulli's equation. So we need, that's why I again and again mention this. Before the application of Bernoulli's equation, we need to make sure that these conditions are rightly satisfied, and or appropriately approximated. Like in that case, as we found out how V1 equals 0, or the flow can ideally taken to be steady in or static in the case of being high, where the depth of the liquid is high in the case of air. So these are some certain assumptions that we make, so that the equation of the Bernoulli's equation remains valid. Okay, this special form, this exclusive form of the Bernoulli's equation, or the most popular form of the Bernoulli's equation, remains valid. So to do that, we need to ensure that these equations these assumptions are rightly satisfied. Okay, so again, this work interaction actually just ensure that these are external work. Okay, additional external work. We may confuse with the pressure work that the flow has to undergo to pass through the channels, but just to mention exclusively, these are the external work. Okay, say shaft work, like that. So okay, so just to keep that in mind. So given that these assumptions are valid, it is only that, and it is only after that we can apply this equation for our particular fluid flow problem. Okay, so we need to know or understand the exclusive nature of this Bernoulli's equation, or this form of the Bernoulli's equation, so that we don't make some silly mistakes while solving fluid flow problems. Okay, so again, we need to just to give the premise of what we are discussing, the extension of the Bernoulli's equation. So we need to just to give you the premise. The thing is that this Bernoulli's equation actually comes from the energy conservation. Okay, energy conservation for fluid flow. Okay. So why okay, again, I will not go through derivation for the sake of saving time, but I just request that, or I will emphasize that you go through the derivations in any standard fluid mechanics book, or again follow the book by Professor Gupta, or just go through this week's and also the last week's video lecture, so that you can get the derivation or idea of how this energy equation is derived. So once you get an idea, you will get to know how this equation, this Bernoulli's equation, or this form of Bernoulli's equation, is actually a very exclusive form, where many terms are neglected or discarded, given that hello, am I audible? Hello Prashant, am I audible? Okay, never mind. So we were discussing that we will see that this form of equation is actually an exclusive form of the energy equation, where certain terms are being neglected or discarded after applying some certain assumptions, and it is only after the successful application of those assumptions that this final form of the Bernoulli equations takes shape. Okay, so the modification or the extension of the Bernoulli equation ideally means that instead of disregarding those additional terms for the energy equation, we are now considering some of those terms step by step, like one after another, so that we can extend the applicability of the Bernoulli's equation. Okay, so ideally it should not be told Bernoulli's equation, but I can say some modified forms of the energy equation. So I should ideally write it as some modified forms of the energy equation. Okay. Equations. Okay. So let me just go through it. So Bernoulli's equation can be extended to include cases where mechanical work is done by the fluid or done on the fluid. Done by the fluid in the case of turbines, or done on the fluid in the case of pumps, right? Where some external work that I was discussing here. Some external work is being done on the fluid so that we could get the necessary output, or the necessary head. In technical terms, it's a necessary head so that the fluid can be pumped or exported or transferred to higher places or higher altitudes. Okay, so in the case of pumps. In the case of turbines, it is the mechanical energy from the fluid that is being extracted so that we could use it to do some additional works, or ideally in most general purpose cases we use it to rotate a turbine so that we can extract some electrical work. Okay, that is ideally the working principle of of dams. Okay, so keeping that in mind, as I was mentioning, work can be done by the fluid in the case of turbine or windmill, or can be done on the fluid in the case of pump or fan. Okay, and whether the work is done on the fluid or by the fluid, that really comes into picture when we are dealing with the sign convention in the energy equation. Okay, so we will look into that. So let's go through it. So again, I guess this example was considered in the video lecture, but I'll just skip past through it very fast so that we can save time and just look into some problems. Okay, so consider a device with one inlet and one outlet. Okay, one inlet and one outlet. Okay, let's and a stirrer is added in this system, and we assume that again the flow is steady, incompressible, in viscid, and there is no heat interaction. But since there is some additional external work being done, so here the external work has to be considered. Okay, so again, since the flow is in viscid, there is no shear forces that is acting in there is no shear forces, since there is no the flow is in viscid. Okay, so there will be no shear forces. So the total rate of work then done by the system is given by minus P1 V1 A1 plus P2 V2 A2 plus Ws, where W dot S, which is the rate of shaft work that is being done by the system. Okay, so it is done by the system. So we are just telling that so that we can fit the equation into particular standard sign convention. Okay, we will just look into it while we are solving problems. Okay, so right now just we just agree with the given convention and let's just go through the derivations. Okay, so here again we consider the energy equation for the CV, where d by dt is equal to dou E by dou t, local rate of change of energy, plus the net efflux of energy. So and that would be equal to Q minus W, because again how it came, because it is basically from the first law of thermodynamics. So just Q minus W. So keeping that in mind, so again E is V square by 2, energy per unit mass, the potential kinetic energy, the potential energy, and the internal energy. Okay. Then for steady flow we get that dou E by dou t is equal to 0, and for no heat interaction we have Q dot equal to 0. Then again, if the dimensions of the say our inlet and outlet are the same, then we get that U inlet is equal to U outlet. Okay, so the net efflux, then this form the equation modifies to that the net efflux of energy would be equal to the net heat interaction minus the net work interaction, or basically the heat supplied to the system minus the work done by the system. Okay, so keeping that in mind, we have net efflux of energy would be given by the net efflux net flux energy flux at the exit minus the net flux of energy at the inlet. Okay, and that would be equal to, since there is no heat interaction, we have Q dot equal to 0 and minus W dot, and since W dot is the work done by the system, so it remains the sign convention within this bracket does not change, but this negative signs comes from the general form of the first conservation equation, first law of thermodynamics that we usually follow. So for that, again I will just reiterate the first law of thermodynamics or any sign convention, that for the first law of thermodynamics, say del E is equal to Q dot minus W dot. Okay, where Q dot is heat input to the system, or ideally I should write net heat input to the system and net work done by the system. Okay, so keeping that idea or that definition for Q dot and W dot in mind, this is the form of the first law of thermodynamics. So since we initially mentioned that this is the net work done by the system, so this term will remain as it is, and the minus sign comes from the general notation that we use in the first law of thermodynamics. So keeping this thing in mind, again from mass conservation we have rho A1 V1 is equal to rho A2 V2. So we have A1 V1 is equal to m dot by rho 1, A2 V2 is equal to m dot by rho 2. Okay, so keeping that in mind, we just modify the equation to finally get V2 square by 2 plus Gz plus P by rho at point 2 or at the exit minus V square by 2 plus Gz plus P by rho at the inlet is at point 1 is equal to minus W dot S, this the net shaft work, this net external work, in this case the net external work that is equal to shaft work divided by the mass flow rate. Okay, so we can just take it as small w dot s. So it is basically small w dot s is net shaft work or net external work per unit mass flow rate. Okay, so then we just to get, this equation is again completely valid. Now if we just try to represent it in terms of head, or represent it in terms of the dimension of length, then we can we divide it by g, small g. Then we have v square by 2g plus z plus p by rho g at 2 is equal to v square by 2g plus z plus p by rho g at 1 minus hs. Okay, so this is the form of equation that we will be dealing with, that we will be mainly dealing with for in today's session. So or the rest of the session that or problems that we are going to use. So again here the thing is shaft work is considered so here for this form of the equation, shaft work is considered and viscous losses are ignored. Okay, viscous losses or viscous dissipation is neglected. Okay, and now again it is told that this form of the equation can be extended even further if we consider the viscous forces as loss of mechanical energy. Basically this viscosity acts as a factor that results in the loss of mechanical energy. So if we take that also into our consideration, we just need to term one more additional term in the right hand side of the equation, so that we can get this additional term into add this equation, so that we can also include the viscous losses. So this is a very standard form, again a very I can say an extended form of the Bernoulli's equation, or a certain particular case of the energy equation where we have considered the viscous losses and the head losses because of external work, but in the case of a steady flow. Okay, so here shaft work is considered, just write it, shaft work is considered, as well as viscous losses or dissipation is also considered. Okay, so again, this is a very important what to say, statement to support the validity of this form of the equation. Okay, so let me just go through it. A general class of fluid mechanical problems, those involving machinery like pumps and turbines, consist of cases where fluid is not exactly steady but changing cyclically. Okay, again, because the fluid is continuously pumped from a lower elevation to a higher elevation, or the fluid is continuously rotating a turbine or the fluid that falls from a higher elevation to a lower elevation, and through that course of flow it rotates a turbine. So since the flow is in continuous motion, and ideally this flow cannot be considered to be steady. Okay, but given the case that if we consider in a case where the flow remains steady, or flow ideally remains steady for each cycle, then this form of the equation remains valid. Okay, so that's why the next statement says that thus the above equation must hold with the understanding that all quantities are now averaged over one rotational cycle. Okay, over a rotational cycle. So keeping these two assumptions in mind, this equation, we can support the validity of this form of the equation in the case of turbo machineries. Okay, it's pump, fans, turbines. Okay, so keeping that in mind, again, there is a discussion about the concept of the hydraulic grade line and energy grade line. So the hydraulic grade line, I'll just again pass through it because it was discussed thoroughly in the video lecture. So just for the sake of understanding, just say we are considering a flow through a venturi meter. Okay, or flow through this converging diverging nozzle. Okay, we'll just write it. Subsonics. So keeping that in mind, we see that these are the various piezometers. Okay, these are the various piezometers that are being set at different pressure taps or different points in the about the surface of the venturi meter, or this is again can be considered to be venturi meter ideally. Say I'm just using it interchangeably. Okay, the converging diverging nozzle and the venturi meter. So say this is a venturi meter, and these are the various points at which the piezometers are attached, so that we can observe the static pressure head. So these points, these liquid levels in the piezometers ideally represents the piezometric head. Okay, piezometric head in the sense that it considers both the pressure head as well as the potential head. Okay, so piezometric heads I represent it as P star, then it will be equal to P, the static pressure, plus rho Gz. Okay, again you can see that this also has the dimension of pressure. Okay. So these liquid levels ideally represents the piezometric pressure head. Okay, and this and the line that joins this this liquid levels through this through these different piezometers, and and thus the locus of these points or the individual levels of water or the fluid in the piezometers can be regarded as the hydraulic grade line. Okay, and just if we now also incorporate the pressure change or the pressure because of the velocity of the fluid, then if we consider that, then that term or that line that represents the effect of velocity as well is termed as the energy grade line. Okay, so that remains constant throughout the flow. Okay, so it will remain constant throughout the flow, so it remains constant. So the energy grade, I must say, ideally represents the total energy. Okay, total energy. Okay, so and again this is again one important what to say point. Both the energy gradient and the hydraulic grade line does not depend on the inclination of the channel. Okay, so this I guess was properly discussed with an appropriate example in the video lecture. So I suggest that you go through it. But just as a matter of fact, since this is very important, I mentioned it in the in this session. Okay, but again, just to say that these differences would incorporate the pressure. Say if you are assuming we consider that this differences include the pressure because of the velocity differences, so you can ideally consider as that C, because in these cases in this region, since say in this region, since area is quite large compared to the region area of the throat, so from the continuity equation for in the case of a steady incompressible flow, we get it A1 V1 equal to A2 V2. So since you consider it as 2 and 1, then since A1 is greater than A2, so it ideally gives that V2 is greater than V1. So basically the pressure because of the velocity at that particular point, right, which is basically termed as a dynamic pressure, that would be higher, or the contribution of that pressure in the contribution of the dynamic pressure would be much higher in the region where the velocity is higher or the static pressure is or the piezometric pressure is lower. Okay, and that's why in this region the contribution because of the dynamic pressure is higher compared to the region that compared to this region. Okay, and that's why this dynamic pressure is higher in this region, and if we just sum it up, it will give us the total energy, right? So keeping that, just concerning the considering the honorary equation, so if it is P plus rho gz plus rho v square by 2, so since this needs to be constant, and this is, so the moment this goes up, this needs to go down, right? So which is clearly being observed here. The dynamic pressure head goes up, so the piezometric pressure goes down. Again in this region, the piezometric pressure head goes up, so the piezometric pressure head goes up and the dynamic pressure head goes down. Okay, that can be observed here. So this is the very concept of the hydraulic and energy grade line. So I hope it was clear. So now we look at the energy balance in the case of pump. Okay, again I told that the modified form of the energy equation or the extension of the energy equation, that is highly applicable in the case of turbo machineries. So we discuss about its applicability in the case of a pump in this case. So I'll just zoom it out so that we can see the diagram. So Just consider the following diagram where this duct extracts the fluid from this particular reservoir, then pumps it out at the point A2, at the point 2. Okay, so just point mark this points as point 1 and point 2, so that there is no confusion. Okay, so here again the pump, what the pump ideally does, it apply some additional work so that it could pump the liquid from a lower elevation to a higher elevation, and what it does is it releases or ejects this fluid as a free jet. Okay, free liquid jet. Ejects the liquid as a free liquid jet. So since it's a free liquid jet, then P2 would be equal to P18. Okay, and then again here, since it is at the surface, then P1 would be equal to P18 as well. Right, so it is just the point is considered just near the surface, just in a free surface. So P1 is equal to P18. So considering this simplification, and say this is Z2 minus Z1 is equal to H, say. So, and P1 is equal to P2, and again we just for the sake of simplicity, we can neglect the viscous losses, so I'll just mention it. Again, here we need to keep in mind that neglecting viscous losses does not mean that the flow is inviscid. Okay, doesn't mean that at all. We are not explicitly mentioning here. Okay, there's nowhere it is told that the flow is inviscid, because since most of our cases it is liquid or this water that we usually pump out, and see it's also applicable for other fluids as well, but for the most general purpose cases, it is water that we usually pump out, and since water is a viscous fluid, so we cannot take the consideration that the flow is inviscid. But again, as I mentioned, as engineers, the order of magnitude of these terms turn out to be very significant in the case of the analysis of this energy equation. Okay, and since we can see here, or we can see here that the order of magnitude of the viscous losses is much less compared to the order of magnitude of the shaft work or losses because of this shaft work. That's why this the losses due to viscous forces can be ideally neglected. Okay, can be ideally neglected. Okay. So these are the things that you need to be conceptually very clear, because you may think that we are pumping water, but we are considering to be inviscid. Then what is the actual validation of this governing equation? Okay, so just to keep that in mind, the order of magnitude. Old equations, order of magnitude. Okay, so keeping that in mind, again we find that V1 is equivalent to 0 because the area of the reservoir is much higher, and the rate at which the liquid level is dropping in the reservoir is very low, so V1 can be ideally taken as 0. Okay, again here V1 is not equal to 0 because there is a certain value of at which the the height of the liquid descends or decreases in the reservoir, but since the reservoir area is so large, this reduction in the height of the liquid is much less compared to the area of the reservoir. That's why we can ideally take V1 to be equivalent to 0. So keeping that assumption, again if we take Z1 as our datum, then Z1 will be equal to 0 and Z2 will be some given height, say in this case it is equal to H. Then P1 is equal to P2, as we told, as it is free liquid jet, then P2 is equal to P18, then again P1 is P18 because the point that we say is just near the surface free surface of the liquid. So now if the mass flow rate is given and the diameter of this ducts are given, and it is also mentioned that the flow can be considered to be incompressible, so in that case we can easily find out V2, right? We just need to apply this round equation. This we know, this are cancelled out, this is taken to be 0, then we can easily find out V2, okay, in terms of all the values that we already know. Now again we follow the same idea, we follow the same equation, and just the notation or the sign convention of the shaft work would change in the case of turbine, because in the case of turbine it will be work done by the system. In the case of pump, it will be work done on the system. So ideally we will observe that in the case of pump, W dot S is work done pump, okay, for pump. It is work done on the system. So this implies W dot S is negative. Okay. Again, in the case of turbine, W dot is equal to work done by the system, because it is now the liquid that falls from a higher elevation that impinges the surface or the vanes of the turbine, which in turn rotates the turbine, that helps in generation of electricity, because that rotation, that mechanical energy is used to rotate an electrical generator. So it is by that we produce electrical power. So since it is liquid that it is the liquid jet or the liquid that does work by the virtue of its potential energy, and that's why it will be work done by the system. So this would imply W dot S is equal to positive. This is the major difference in the case of the sign convention for the shaft work in the modified boundary equation. Okay. Here again, here just we look at a diagram. So it is a very simplified diagram where this circle denotes the turbine, and it is the liquid is being extracted or to the help of a penstock, where the liquid traverses to the penstock. So I guess I can draw it also, just to be clear. In the reservoir, the liquid traverses through the penstock, and then it will hit the turbine, then it will cause the turbine to rotate, and then this liquid moves out at the exit. So okay, and again we apply, keeping that in mind, we take this blue dotted line as our control volume, and then here we see that let HS be the head extracted by the turbine and converted into work. Okay. Again, neglecting the viscous losses, because the order of magnitude of viscous losses is much less compared to the shaft work that is being obtained from the potential energy of the water or the fluid. The engineering boundary equation or the modified boundary equation is another name, just another fancy name for it. The engineering boundary equation can be written as V square by 2g plus z plus p by rho g at point 2 is equal to V square by 2g plus z plus p by rho g minus hs and minus hl. So this will be equal to 0. Okay. So again, from the given geometry, we see that V1 can again be ideally taken to be 0. In fact, in ideal case, this can be taken to be 0, because say if we are extracting water from a reservoir, okay, and even if we are extracting the water from the reservoir at a particular volume flow rate, it may happen that this reservoir is being supplied or is being filled by the help of some rivers or other sources that keeps the water level in the reservoir to be constant. And keeping that idea in mind, then V1 can exactly be taken as equal to 0, okay, at point 1 at the free surface, right? Then again z1 is equal to h, then z2 if we take it as 0, then at the as our datum, so z2 is equal to 0, then p1 equal to p2. Again the liquid is pumped as a free jet, so p1 is equal to p2, then that will be equal to patm. So keeping that in mind, we would have v square by 2g is equal to h minus hs, okay. And if you want to find out the value of the head loss or head extracted in the case of turbine, hs would be a positive quantity and it will be given by h minus v square by 2g, okay, where h is the elevation from which the fluid pours down through the penstock on the vanes of the turbine, okay, vanes, just to write it, vanes, these are the vanes, okay. I guess should denote it here, here itself, vanes. Okay, so the net power output will be given by so since we know that W dot S is equal to M dot W dot S again, so and again we told that HS is the what to say, shaft work per unit, it is represented in terms of in the unit of length, so it was divided by g, okay. So since it was divided by g, so sorry, it will be m dot g into hs, right? So m dot is the mass flow rate, so mass flow rate is equal to rho av, and g is this, and sorry, and if we just take h out of this, the h common from this equation, then we get hs is equal to h in bracket 1 minus v square by 2gh, okay. So here just to make sure, I'll just write it, hs is equal to small w dot s by g. I guess I mentioned it in the session, and again this was also mentioned by Professor Gupta, so just you check it, okay. Yes. Okay, so here you see that the term 1 minus v square by 2gh represents the fraction of total available head extracted by the turbine, okay. So this is the total head that is being extracted by the turbine from the net available head that was available for use, okay. Because since if we had h as the total potential energy head, h was the total potential energy head, it is the energy by the virtue of potential energy by the virtue of its elevation from the ground, right? Then we have only h 1 minus v square by 2gh, the net head extracted. Even after considering so many ideal scenarios, we can only obtain a fraction of total potential energy head that is being available to us, okay. So that is what is being signified by this fraction here. So and here it cannot be positive because v square h is positive, g is positive, and v square, since it is a square term, it will always be positive. So this term will always be lesser than 1. So this will always be only a fraction of energy that we can obtain in the case of a turbine, okay, not the entire. And also this also there will be various certain other modifications that we need to check the various viscous losses, mechanical losses that we need to check for in the case of the turbines. There will be various mechanical losses in the shaft, and while rotation of the shaft there will be various mechanical losses. So these are things that we need to consider. Again, if we couple this shaft with generator, again the generator would have certain losses, right? So considering this, all these losses, there will only remain a very fraction of energy, total potential energy that we are able to obtain in the form of electrical energy from the net energy that is being available to us, because by the virtue of the potential head of the fluid at a certain elevation. Okay, so that is I wanted to tell you. This is the what to say. This is how this this is the basic idea or the basic working principle of any turbine. Okay, and in the we also discussed the basic working principle of pumps. Okay, we will discuss some problems. So where these equations or these form of the equations will come in handy. So it is suggested that you remember this form of the equations, this one in the case of pump as well, and as also keep in mind the sign convention, where in which case Hs will be positive, Hs will be negative. It is quite obvious that Hs will be negative in the case of pump, and in the case of turbine it will be positive. Okay, so that thing you need to keep in mind while solving any numerical problem. So we'll look upon some problems in today's session, but it is quite wise if you have already these sign conventions imprinted in your head. Okay, so this I guess we will discuss. So let's not okay, then flow in ducted fan. Okay, so again this fan, this another turbo machinery, fans that we are discussing, fans, turbines and pumps. So fan is another turbo machinery that can be used to generate flow at higher velocities. That is ideally the working principle of many wind turbines or in the various wind laboratories. So it is by the help of such fans, such suction fans, by the virtue of which they can generate the required flow through the wind tunnels. Okay, so here again we see that the expected velocity of air is not very large and the flow can be considered as incompressible. Okay, yes, so for most of the wind tunnels that we use for our day-to-day for our most of our wind tunnel experiments that we do, say we flow over a airfoil, flow over some bluff bodies, these are in the subsonic regime. So in the subsonic regime, the flow can be ideally taken as incompressible. Okay, I am not saying at all that there is no applicability of supersonic wind tunnels. Yes, there is supersonic wind tunnels that exist, but for in this case, the present geometry or the present context that we are talking about, or also the wind tunnel example that was mentioned by Professor Gupta, those wind tunnels that we discussed were ideally subsonic wind tunnels. Okay, very low velocity, and in that regime, the flow can be ideally taken to be as incompressible. So this is what we meant by that. So flow can ideally be taken as incompressible. Again, this previous assumption that we discussed, that averaged over one rotation of the fan, the flow can be taken as steady. Okay. So again, with the neglect of viscous losses, the modified Bernoulli's equation takes the form v square by 2g plus z plus p by rho g at point 2 is equal to v square by 2g plus z plus p by rho g at point 1 minus hs. Okay, hs we need to see what would be its sign convention. Okay, so we clearly get an idea that it should be or it should not be positive or negative. Okay, we'll get into that. So here, since point 1 and point 2 both lie on the same elevation, so these both of terms can be cancelled out. Then again, pressure at point 1 and at point 2 is both are at atmospheric pressure. So the point at which the point from which the air is being sucked and the point at which the air is being released are both, since both are at atmospheric pressure, so both I should write it, I guess, Z1 equal to Z2, P1 equal to P2 equal to P atm. since this is the scenario, these terms also cancel out. Okay, and V1 square, if we ideally assume that the flow at the inlet is stationary, because it is the turbo machinery, that is a fan that is being used to suck the flow and generate flow within the duct. So the velocity at point 1, if it is considered to be at a certain distance away from the inlet, it is from this control surface, it is assumed to be at a certain distance, so that the flow remains uniform, or in this case stationary. So V1 can be ideally be taken as equal to 0. Again, I will say equivalent to 0. Or again, you can use the concept of order of magnitude. So order of magnitude of V1 is much less than order of magnitude of V2. So keeping that in mind, V2 is also, V1 is also equivalent to 0. So we only remain with V square by 2G is equal to minus HS. So we have V square is equal to minus 2G HS. Again, now, by the looks of the equation itself, you can clearly say that in the case of fans, HS would be negative. Why? Because G is a positive quantity. V square would be positive because it is square. So to maintain the homogeneity of the signs in both the sides of the equation, HS must be negative, and that's why it is, for the case of fans, work is done on the system. Work is done on the system. Okay. So again, this is up to which what I wanted to discuss. So we will now just go through some problems that applies the concept that we discussed today. So I will take since we are out of time for today, we will take two problems that discusses the applicability of the concept that we have discussed. So let's just go through that questions. Okay, just zoom out a bit. So consider a common household pump used for lifting water. Okay, pump. It draws up water from a I'm sorry, say from a reservoir. Okay, I just line. Okay, from a line. It draws the water from a line or reservoir and delivers it at 0.2 meter higher at an enhanced pressure. Okay, it is given that P2 minus P1 is equal to 0.1 megapascal. Okay, it would be better if we just read the question along with by looking at the diagram. So it is given that P2 minus P1 is equal to 0.1 megapascal. So pressure is enhanced after the application of the pump, which means that it adds some additional pressure energy to the flow. Okay, so P2 minus P1 is equal to 0.1 megapascal. The volume flow rate is 0.01 meter cube per second. Okay, if the power consumption is 1.5 kilowatt, so the question explicitly gives the idea that the power is being consumed by the system. So work is done on the system. So it will basically mean that the Ws term or the Hs term that in our modified boundary equation would be negative. Okay, and so if the power consumption is 1.5 kilowatt, we need to find the viscous losses. Okay, again, neglect purely mechanical losses in transmission and bearing. As I told, there can be various losses in the case of fluid flows. We are only discussing some portion of it, so there can also be mechanical losses because of transmission and bearings, because of the very structure of the pump, right? It will have some veins, and because of the friction in the veins and the brushes, there can be some mechanical losses in that also. So we are neglecting that, right? In the bearings, sorry, brushes as well, in bearing, right? So there can be some mechanical friction in the bearings itself. So there can be some mechanical losses. So we are asked to neglect that. Okay, neglect the mechanical losses. Okay, So here for the current scenario, okay, we choose a CV coinciding in the inside boundary of the pump casing. Okay, so this is the CV that we are going to choose by the this blue dotted line, and intersecting the inlet and outlet at the sections normally. Okay, so inlet and outlet. Okay, so it is again told that it is given the diameter at inlet is 10 centimeter and at the outlet is 2 centimeter, and the liquid is being pumped at a higher elevation where at elevation where the point 2 is at a height of 2 meter with respect to point 1. Okay, so keeping that in mind, so we just now we just need to again deal with the same equation. I'll just write it again beforehand. So P by rho g plus V square by 2g plus Z1 Z at point 1, sorry at point 2 is equal to P by rho g plus V square by 2g plus Z at point 1 minus HS minus HS. So we need to find HF. Every other parameter is being given, so we just need to find the value of these parameters. Okay, so V1 is V1 you can find since the volume fluid is given and the flow can be taken as, say I will say rho is in a constant. So V1 is equal to 0.01 by pi by 4 into 0.1 square. This is basically the radius of the diameter of the inlet. So we get V1 is equal to 1.27 meters per second. Now since we are dealing with the equation in terms of the head, there's a velocity head, pressure head, potential head, or the head of losses because of the shaft, or head losses because of the viscous dissipation. So we are dealing with the energy equation in terms of the heads. So or in terms of the dimension of the length. So I did to just to make our calculations much simpler. We just now directly calculate the velocity head at the inlet. So we get V1 square by 2g is equal to 0.0822 meter. So we can just use a calculator and find the value. So V1 square by 2 is equal to 0.822 meter. Then V2 is equal to 0.01, again same. We know the volume fluid, it remains constant. So 0.01 V pi by 4 is 0.01 divided by pi by 4 into 0.05 square is equal to 5.0 meter per second. Okay, quite obvious, since the volume fluid is same and the duct dimension is reducing, the volume velocity will increase, right? Just cross checking or verifying our concept of mass conservation. Okay, so we need to check that because mass conservation needs to be valid, right? And V2 square by 2g is equal to 1.32 meter, right? So we again evaluate the velocity head at the exit. Now we need to evaluate the head losses because of the shaft work. Okay, so see as this equation was again H is equal to W by G. I guess this is again rectified. That was quite doubtful in the previous section. So just to rectify this, H is equal to W dot S by G. Okay, just to confirm. Okay, so again we need to evaluate HS. So HS can be given by H is equal to W, small ws by G. So small w is again given by capital Ws by the mass flow rate divided by mass flow rate into G. So here again I'm sorry, this will have a minus sign. So minus, since why minus? Because the work is being done on the system, right? The pump, we are applying additional electrical, we are using electrical work to rotate the pump so that we can apply some energy to the fluid so that fluid can be pumped at a higher elevation. So work is done on the system. That's why we will have the shaft work as negative. So keeping that in mind, so it is given that is 1.5 kilowatt. So converting into watt, again then mass flow rate can be given by density. So write it, density into the volume flow rate. So 1000 into 0.01 into 1 into 9.81, which is basically the value of G, acceleration due to gravity. So once we evaluate that, we get that the head loss because of shaft work is equal to minus 15.92 meter, 15.29 meter. Okay, Again we evaluate the pressure heads or the difference in the pressure head because of the pump. So we get that P2 minus P1 divided by rho g. So we get 0.1 into 10 to the power 6. Since it was given that the P2 minus P1 is equal to 0.1 megapascal. So it is 0.1 into 10 to the power 6 divided by 1000 into 9.81. So we get that after evaluating that, we get that P2 minus P1 rho g is equal to 10.19 meter. Okay. Again Z2 measure also, this is already given in the equation. So we just need to do is we need to plug these values in this equation and evaluate the value of HL. So after we do that, we get that HL is equal to 1.86 meters. Okay, the head loss because of the viscous dissipation. Now we need to find out the net work or the power loss due to the viscous losses. So again we get that W dot L is equal to HL M dot G. Okay, just this one, this equation itself, right? From this equation, that is HL is equal to capital W L dot M dot G. So from that this equation we just evaluate the capital W dot L. So we get it is 182.31. So you can clearly see that even if in this case it was not explicitly mentioned that the head loss because of the viscous losses are not that significant, and in fact it was asked to find out, we can clearly see that it is comparatively lower. Okay, see, it is not negative, but still it is lower than the head loss because of the shaft work or the net shaft work. So you can clearly see how at least in the case of the case where the duct lengths are quite small, or the duct lengths through which the liquid flows, or the dimension of the lengths of the pipes at the inlet and outlet is quite small. In those cases the viscous losses are quite significantly lesser than the shaft work that has to be given as an input to the pump, so the the fluid can be transferred to a higher elevation. Okay, so this we can again verify. So it is in fact the order of 1/10 of the shaft work. Okay, so order of W dot L is equivalent to order of W dot S by 10. Okay. Just to again, so similar to that, now again we take a question on a turbine. So we look at this question. So again, just go to we just go to the question. So water from behind the dam passes through the penstock and runs a turbine. Okay. If the difference in elevation between the reservoir level and the discharge point is h, find the maximum power the turbine can generate for a given penstock diameter. Okay. So basically, so here it is told that point h1, point 1 and point 2 differ by distance by elevation h. So here you can actually write as so it will basically be Z2 minus Z1 is equal to h. Okay, we then apply the same equation, so I am not writing the equation again. And P1 equal to P2 is equal to P18. Why? Again I told that pressure at this point is the atmospheric pressure. Then again the liquid that is being released or ejected out from the turbine is ejected out as a free jet. So the pressure at that point will be again be equal to the atmospheric pressure. So P1 is equal to P2 is equal to P18. Okay. So again V1 can be ideally be taken as 0, right? So keeping those assumptions or these things in consideration, we apply we plug these values into the modified boundary equation or the engineering boundary equation or the modified energy equation, anything you want to tell it. So we get that V2 square by 2 plus 0 because Z2 is 0 plus P ATM by rho is equal to 0, again V1 is 0, plus GH because Z1 is respect to the datum, it is at height h. So I'm sorry, it will be z1 minus z. So since it is at height h, so we have gh plus p atm by rho. Then we have minus the shaft work and the viscous losses. Okay, so keeping that in mind, again you can clearly cancel out both these pressure terms. So again it is exactly mentioned here, right? Then we have this equation can be written as Ws is equal to gh minus v square by v2 square by 2 minus Wl. Again, as I told, in the case of turbines and pumps, the choice of the control volume or the design itself makes it a viable conclusion, or a, what to say, a proper conclusion that the head loss due to viscous dissipation is comparatively lower or much lower than the head loss because of shaft work, right? Or head addition or head extraction of because of the shaft work. So keeping that in mind, we have that since if we assume that WL is much lower than GH, then and obviously V2 square by 2, say considering the order of magnitude of both the terms in this equation, so we can have Ws is equal to GH minus V2 square by 2. Okay, so keeping that in mind, we have that capital Ws would be equal to the mass flow rate into the small ws, right, into this, right? So m dot is equal to rho av at 2 at one any point. So ideally, so since v1 is almost equivalent to 0 in the case of inlet, so just to ignore the discrepancy, and since also we don't know the area of the reservoir, usually we don't have an explicit idea of the area of the reservoir, so it is better that we take the this mass flow rate measured at the exit, right, where the dimensions of the duct as well as the velocity is known, right? So keeping that in mind, m dot is equal to rho av at point 2 into ws, right? So it can be again written as rho into a2. We just take then we just multiply v to both these terms, so it is gh v2 minus v2 cube by 2. Okay, so we are asked that we need to find the velocity of the at the exit for which we have the highest maximum power extraction, okay, or maximum power that can be obtained, right? So in order to have that, the first derivative, or dws dot by dws by dv2 should be equal to 0, right, for maximum. So this is exactly written here. So in order to have that, we take the first derivative of the net shaft work with respect to the velocity at the exit, right? So we get that since this is constant, we can just take the derivative of this term in the brackets. So we have gh minus 3 v2 cube v2 star square by 2 equal to 0. So if we equate that, we get v2 star is equal to square root of 2 by 3 gh. And if we want to find the maximum power, we just need to substitute the value of v2 in this expression. Then we finally get ws max is equal to rho a2 into 2 by 3 gh to the power 3 by 2. So this is the maximum power that can be obtained in the case of in the case of a turbine, right? So this is done. So there are some more problems again that could have been discussed, but again these are some of the problems on for the basic application of Bernoulli's equation that has been discussed. So again, in this case we are discussing about siphon. So basic working principle of siphon and the governing equation that governs its how the siphon works has been discussed in a previous session. So I suggest that you can go through this problem, since I will be sharing this PDF in the this PDF is available in the course website in the NPTEL. So you can go through these examples. That will be quite beneficial, because I don't think I will be discussing in the next session. So you can just go through these examples and just for as help or reference, you can go through the example. That will be helpful for you to solve some certain problems in the assignments. Okay, just for the sake of simplicity, since we didn't discuss some numerical problems on siphon, I will just go through this example. Okay, it's quite simple again. I will just go to the question. So a U tube acts as a water siphon. Okay, the bend in the tube is 1 meter above the water surface. 1 meter above the water surface. The tube outlet is 7 meters below the water surface. So, okay, the water issues from the bottom of the siphon as a free jet at atmospheric pressure. Determine the speed of the free jet. Also determine the pressure, absolute pressure of the water in the bend. Okay, so we need to find the velocity at which the water exits as a free jet from this outlet. Secondly, we need to find the pressure at this bend. Okay, the absolute pressure at this bend. Okay. So for the first case, since we need to find the velocity at the free jet, the ideal choices of points in our system would be, first point should be at the free surface of the liquid near a siphon, and at the end of a siphon. And secondly, actually this this depth should be quite low for the applicability or the approximation that V1 is equal to velocity at the free surface. So that's right. So keeping that in mind, we choose 2 points. It is one at the free surface and one at the exit. So keeping that with the choice of these points, we apply the Bernoulli's equation along a streamline. Okay, we have to assume a streamline that exists at this point. Okay. We assume that point 1 and point 2 lie in the same streamline, and applying Bernoulli's equation, we get P1 and P2 is equal to the same. Then these two terms cancel out. These two terms will go out. Again, V1 is equal to 0 because the rate at which the height of the liquid goes down in the reservoir is quite small. So V1 can be taken as ideally to be 0. So we have V2 square by 2 is equal to GZ1 minus GZ2. And we have that this is 7 meter below the water surface, right? So we have V2 is equal to 2G into 7, right? 7. 2 into 9.81 into 7. So we ideally get V2 is equal to 11.7 meter per second. Again, we are asked that we need to find the absolute pressure of the water at this point, at the bend. Okay, so it's not mentioned at where, so we are just taking at the center of the bend. Okay, just for our sake of our simplicity. So we are not encountering this losses, and we need not need to consider losses at this bend. So we are safely choosing a point at the center of this bend. So say we denote it as point A. Okay, so for again to find the pressure at this point A, we again apply the Bernoulli's equation at point 1 and point A. So we have that after applying Bernoulli's equation, we get that PA by rho is equal to G Z1 minus ZA minus VA square by 2. Okay, it is again simplified, so I don't want to go from the equation from the scratch. Once you apply write the full Bernoulli's equation, just cancel out the terms, and you will get this form of equation. Okay, so this PA by rho is PA. Okay, not P atmosphere. It is P pressure at point A. Okay, at this point. So PA by rho is equal to GZ1 minus ZA minus VA square by 2. Then we have that the point A was at an elevation of 1 meter from the free surface of liquid. So Z1 minus ZA will give us -1, and VA we already find out. VA should be equal to V2 because the area of the duct remains constant. So VA is equal to V2. Just write it for simplicity. VA equal to V2. So just plug in those values, we get that PA is equal to 78225 Pascal, which is the gauge pressure. But we are asked that we need to find the absolute pressure. So we just add this pressure with the atmospheric pressure that we have 101325, so we get that PA absolute at pressure at the absolute pressure at point A is equal to 23.1 kilopascal. So again, so I guess that will be it for today's session. So there are some more problems in this PDF that I will be sharing, so you can just go through the PDF for your reference and just check whether we are able to solve similar problems that will be in the assignments. So just look into that. And again, I emphasize you that you go through the you attend the Monday's session. That will be quite beneficial for you, because there may be some concepts or doubts that I may not have been able to clarify. So that the TA that will take the session on Monday will take the session on the same topic, so you can clarify your doubts then. And also, once again, I suggest that please go through the video lectures by Professor Gupta thoroughly again and again if you have any doubts, because they are the best sources for us to get our doubts clarified and learn our concept in the best way possible. Okay, then thank you once again. So that will be all for today from my side. So thank you and have a good night.